This is Chemistry Section 2.2, Part 4.
Okay, so we are starting today's lesson with a review from Bohr diagrams, which are a review from Science 9. However, I'm going to go through it as if you haven't or have a vague idea of what it is, but you don't fully remember what it is. So a Bohr diagram shows how many electrons appear in each electron shell around an atom. Electrons in the outermost shell are called valence electrons, and these are what are involved in chemical reactions between the elements. Think of shells as being 3D-like spheres, not 2D-like circles. So we just draw them as flat 2D structures to make it easier to draw. So this is an example Bohr model here for chlorine, and then you can see that it has 1, 2, 3 shells. The first shell contains 2, the second shell contains 8, and the third shell contains 7, which if you add that up together will give you 17 electrons, which is related to the fact that this is an atom of chlorine which has 17 protons. Okay, what element is this? So if we are to count the number of electrons present, we have 2 in the first shell, 8 in the second shell, so that brings us to 10, and then another 2, 4, 6, sorry, I should have circled that before, 8. So we've got a total of 18 electrons, full valence outer shell. 18 electrons tells us we are dealing with argon. So it has a 2 plus 8 plus 8 electrons. They're 18. Therefore, we can assume this is an atom because we haven't been told otherwise. So it has 18 protons. It has 3 electron shells, so we know it's in period 3. So that is the third row. And then it has 8 outer valence electrons, which is a full shell. So we know that this is in the last group. So we are dealing with argon. Okay, so you use both the periods and the number of valence electrons to tell us what element we are dealing with quickly, or you draw out the structure to determine it based on the number of electrons present. So patterns of electron arrangements in periods and groups. So electrons appear in shells in a very predictable manner. There is a maximum of 2 electrons in the first shell, 8 electrons in the second shell, and 8 electrons in the third shell. The period number, which are these over here, so the rows going across, going that way, are equal to the number of shells in an atom. Except for the transition elements, which you can notice are removed here, or do not show up basically after calcium, which is where they would be present. So except for the transition elements, the last digit of the group number equals the number of electrons in the valence shell. So for example, when you're looking at something like 13, we look at the 3, and that's how many electrons are in the outer valence shell. So if you look at boron here, it has 1, 2, 3 electrons. Same here with carbon, it has 1, 2, 3, 4 valence electrons, and so on. So this second number, or the first number in these cases, tells us the valence electrons, where if we look at this, which tells us we have 1 shell. Here we have 1, 2 shells, 1, 2, 3 shells, 1, 2, 3, 4 shells. Okay, so use these things to help you to draw your Bohr models more easily or to predict the element based on the Bohr model. It is important to know that noble gas elements have full electron shells and are very stable, meaning that they are non-reactive. So they should have 8 valence electrons, with the exception of helium, which only has 1 shell, and that first shell can only contain 2 electrons. So it is happy and has a full valence shell with just those 2 electrons in the first shell. All others have 8 electrons in their valence shell. Next, we have a super bad chemistry pun slide for noble gases relating to the fact that they do not react well, that they're really stable elements. Okay, so let's do a little bit of practice with Bohr models now. So I'm going to do the first and the last example, and then you can fill in the rest for these. I have drawn at the top examples of what it would look like on the periodic table. However, it's probably easier if you use your own periodic table for this. So starting off with neon, which has the atomic number of 10. So we want to start off by just filling in the information that would be in the nucleus. So we've got neon, which is Ne. It has, based on the atomic number, 10 protons. And using the mass number, which is 20, if we do 20 minus 10 equals neutrons. So that is mass minus the atomic number. So that means we have 10 neutrons. And we symbolize that with n naught, so n to the power of 0 essentially. So this is our nucleus. Our nucleus is not our first shell, so we then want to draw one shell around it. This first shell contains 2 out of the 10 electrons, so we have 8 left over. So 1, 2, 3, 4, 5, 6, 7, 8. So moving around, kind of keeping the electrons paired more for you to keep track of them, keep them paired, and you should have a total of 10 electrons if you were to count those out, which we do. Now, that was for an atom, as shown here. Now we're dealing with a sodium ion. So sodium has an atomic number of 11, meaning it has 11 protons. So we're going to follow the same steps for the beginning. So sodium, symbol Na. It has 11 protons. We're going to look at the mass, and it is 23 minus 11, giving us a total of 12 neutrons. So again, we've got our nucleus. We'll fill in our electrons. So that's 2. Now the plus here means that it is missing 1 electron. So instead of having 11 electrons like the atom would, the ion is going to have 10 electrons. So it's going to look like neon. So we've already done 2, so we have 8 other electrons to place. Okay, and now to make sure you identify the fact that this is an ion and that you just haven't forgotten to draw 1 electron, we symbolize the ion by putting square brackets around it. And then the charge, so that's the finished sodium ion. Okay, so I would like you to pause here and fill in the remaining atoms and ion Bohr models.